Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 3A, such as Logistic Regression. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. In this video of Part 3A, we will discuss following 14 important parts of logistic regression into steps.
Alright, let's do this. Logistic regression intuition. And you can probably already tell by my voice that I'm pretty excited. There's some very interesting slides coming up, and this is quite an important topic. But at the same time, it is quite challenging. So a quick heads up, there will be some math, and I've done a few run-throughs of this presentation already, and I will try my best to convey everything in the simplest way possible. So let's get into it. We already know about the linear regression. We know that there's a simple linear regression and it has this very short formula with one independent variable, and we also have looked into the multiple linear regression, which has many independent variables. So we already know how to deal with this type of challenge. So when we have a scatter plot like that, where on the horizontal axis we've got the independent variable, on the vertical axis we've got the dependent variable, and this is an example we looked at: salary versus experience. How do we create a model here? So we use a simple linear regression. It puts a line through our data, and that line is modeling our observations. So we can basically forecast things and compare our actual observations to our model and so on. So we know how to deal with challenges like that, or problems like that. But your company that hired you as a data scientist, what they do is they send out email offers to customers with like a proposal to buy certain products. It might be a clothing store, it might be a grocery store or something like that. So what they do is basically they send out a offer in email to a lot of customers to purchase a certain product, and here you've got a sample of those customers that they contacted recently. You've got their age, and also you have a variable whether or not they took action. So did the person take up an action, perform an action? Did they take up an offer? Did they buy a product? Did they open up an email, respond to our email, and so on? So was the action taken or not? And very black and white, very different. But at the same time, like, even though we don't know what to do, we don't know what's going on here, it's not what we're expecting, but at the same time, intuitively, we can see that there is some sort of correlation. We can see that the observations on the bottom, they're a bit more to the left, observations on the top are a bit more to the right, implying kind of that probably older people are more likely to take action based on this offer, and younger people are more likely to ignore it. So, can we somehow model this? How about we try the existing method in our toolkit, which is the linear regression. Let's run a linear regression, and that's what it looks like. As you can tell, it doesn't look like the best approach, doesn't look like the best method to solve this problem. So let's look into this in a bit more detail. We're going to draw the other horizontal line over here. Instead of trying to predict exactly what's going to happen for any given person, let's imagine a person, and let's say we want to predict for that person, knowing their age, we want to predict whether they will take up the offer or not. But instead of predicting exactly whether they're going to take it up or not, how about instead we will predict the probability. We will state a probability or a likelihood of that person taking up that offer. And if you think of it in that way, right away things start becoming clearer. Right away you can see that, okay, so this chart is actually from 0 to 1. And I also know that probabilities are from 0 to 1. Oh, that's interesting. So basically I could fit in probabilities between 0 and 1. The fact that the red dots, the red observations are already either 0 or 1 and nowhere in between, well, that's simply because we already know the result. We already know that they're either there or there. But for something that we're predicting, it kind of makes sense to say, well, I don't know for sure, I don't know 100% he'll take it up or not, but I know maybe maybe with an 80% chance you'll take it up or not, right? And when you think of it that way, the linear regression line, or at least that part that's in the middle between 0 and 1, it makes sense, right? Well, it makes some sense, because that is basically, it's telling you that anybody between those ages of, for instance, where it's crossing the horizontal line for the first time, it might be, or where it's crossing the horizontal axis, it might be like 25, or let's say 35, and where it's crossing the horizontal axis for 1, it might be, let's say 55. So those people between 35 and 55, they, anything in between, any person that falls in between that age, there is a probability of them taking up this offer, and that probability is increasing as we move to the right. As we take more and more older people, that probability is increasing. So the part of the linear regression in the middle kind of makes sense, and we can do something with it. But the parts that don't make sense at all are the ones at the top or at the bottom, because a probability can never be less than 0, it can never be above 1. So what is the linear regression trying to give us a hint about here? Well, what it's probably saying, what we could interpret it as, is that people above that age, that nominal age, we said 55, above that age, they are very, very likely to take the offer, actually more than 100%. So basically, they're definitely taking it up. Anybody below 35 on the other side, on the left, they're definitely not taking it. So essentially what we're saying is, if we ever take that approach, then we would have to replace this linear regression line with a line that looks like that. So let's just cut those bits off and replace them with horizontal parts. And that would be a very basic, but it still would be an attempt at creating a model for this situation. So we would still be able to use this to make some sort of predictions and assumptions that talk about the correlation between the action and the age of a person. So that's a very basic understanding, and that's kind of the start of our understanding of intuition behind logistic regression. So let's see what the actual scientific approach is. So here we've got the line that we looked at, and it is described by this equation. Now this part is going to be, this is the most fun part, so bear with me. If you apply to this equation a sigmoid function, which looks like that, so you put the y into the sigmoid function in purple, and then you solve for y from the purple box and you put y back into the blue box, then you will get the green box. So basically your linear regression will start to look like this. And this is the formula for logistic regression. And what that will do to a chart, which is most importantly this visual part, it'll convert it from the chart that we see at the top to this new chart, which is actually the logistic regression function. So if at this stage you're asking yourself what just happened, then you're not alone. The first time I saw this, or I learned this was the expression on my face. If you're totally comfortable with all of that, that's super great. That means you'll fly through this section. But if you're confused right now, not a problem. I was the same when I was in your shoes. So let's take this step by step. Let's look at it step by step, exactly what happened. So there's our graph. There's our independent variable. There's our outcome, yes or no. So that's the y, the dependent variable. And there are our observations in our data set. Based on these observations, and plus using this formula, which we're going to take as given, this is the logistic regression formula. Using this formula and these observations, we come up with this line. And what is important to understand here, it's not a magical line. This line for the logistic regression is the same as a slope or a trend line for a linear regression. So basically what this line is doing is it is using the formula, it's following the formula, and it's the best fitting line that can fit these data sets. So basically we're doing exactly the same thing as with a linear regression, but it just looks different. That's all. So there are heaps of these lines that you can draw that look like that, but only one of them is the best fitting line. So the point of the logistic regression is to find that best fitting line, and this is it. So we found the best fitting line that follows that equation and fits these variables that or these observations that we had in our data set. After that, we can forget about the equation, we forget about the variables. We've got our line. So this is our logistic regression function. We've found it. Same thing as with the linear regression. We've created the model. We've built the model. You can see it. This is the model in front of you right there. Now, what can we do with this logistic regression? Well, we can use it to predict probabilities. And we've already touched on probabilities, that they lie between 0 and 1, and that instead of predicting for sure that something will or will not happen, how about we predict probability? So let's look at, oh, by the way, probability here is called p hat, so that's a little sign above p gives it the name p hat, and anything you see in the with a hat in this section just basically means that it's something we're predicting. So and that's a way to remember it, that picture p hat. So we're predicting this probability. Okay, so let's take 4 random values for the independent variable. For x, we're going to say 20, 30, 40, 50. Let's see what happens to these variables. So let's put them on the x line. Those are the dots, and I specifically put dots, not x's or crosses, because it doesn't mean that they're on the horizontal, the bottom line doesn't mean that their probability is 0 or that their dependent variable is 0. No, they're just there because they're on the x-axis. We just plotted them there. It has nothing to do with the vertical axis. Now, what you need to do to find the probabilities is you need to project these values onto your curve. Once you project them, you get these blue dots or blue observations, which plotted basically. So these are the fitted values. As you remember, in Gretel you have, in red you have the actual, and in blue you have the fitted values. So these are your fitted values. And now, if you project them, if you want the probabilities, you need to project them to the left, like that. And let's have a look at these probabilities. So the person who's 20 years old, the probability of taking up this offer is very low, perhaps 0.7%, so less than 1% to take up this offer. The person who's 30 years old, the probability is higher, it's about 23% to take up this offer. The person who's 40 years old, their probability to take up this offer is 85% according to this model. And the person who's 50 years old, their probability is 99.4%. So that's the first thing that you can get out of logistic regression. That's what we're going to be using it very actively when we're talking about building geodemographic segmentations, because you use this probability as a score, and I will talk about this more. So you can actually rank people, who is the most likeliest to take up your offer and who's the least likeliest to take your offer up. So it's actually even better than just having a 1 or a 0. You have a probability, so you can order people by this probability. Anyway, you might want to say, well, I don't want the probability, I want a prediction, as because this is a regression, I want a prediction for the y value. So okay, we can do that. Can we get let's get rid of those probabilities. Now, can we get the actual? Well, obviously we can't get the actual, because the actual is something that we can only observe in our data set or in real life. We can only get a prediction for the actual. So y hat, as the hat suggests, is the predicted value for the dependent variable. How do you get y hat? Well, the approach is very arbitrary. You have to select a line. Let's wait for that. Okay, so you have to select a line. In this case, we're going to select 50%. You can select it anywhere, but 50% is usually selected because it's in the middle, and therefore you have symmetry. And anything below this line, so anything that falls on the curve below this line, will be projected downwards onto the 0 line, which makes sense. So it's basically saying if your predicted probability of taking up this offer is less than 50%, let's say it's 40% or 20%, then we're just going to say that you're probably not going to take up this offer. And so that's what's happening. The person with 0.7%, the person with whatever it was, 27%, 23%, their probabilities are not 0, but they're below 50. So if you do require a y hat, so a predicted value, a yes/no value, then makes sense that if something's below 50%, you're probably going to say that they're not going to take up the offer. Now anything up, oh yeah, so there you go. Both of them y hats are 0. Now anything above the horizontal line that we've selected, the 50% line, it is agreed that all of those values that fall onto the curve above that line are projected upwards. They're projected onto the yes line, the 1 line. So the person that's had a probability of 85% is projected outwards, and the person that had the probability of 99.7% is projected upwards. Also makes sense, right? So if somebody's got a chance, you're predicting that somebody's probability of taking up an offer is 85%, then if you have to say yes or no, then you're probably going to say yes. You're going to say yes, this person will take up the offer if you have to choose one of the two. So those are our predicted y hat values. In this case, they're both 1 for those two variables. And those are the two things you can get out of the logistic regression. So you get the probabilities, which are important. Also, you can get the y hats, so the predicted values for the dependent variables. Once again, it's important to think of it as it's doing exactly the same thing as a linear regression. It's fitting this line, even though it's not a straight line, and the values are not scattered. Everything looks bizarre in its uniformity, or in the way its structure makes it look very bizarre. But still, it's pretty much the same way. We've agreed on a line or a formula for a curve, and we're trying to fit the best curve to our data. Once we've done that, we've got a model, we've got the coefficients, which we'll talk about later, and we can start drawing conclusions or insights from this model. And some of the insights are we can get a probability of somebody taking action or of the event occurring, and or basically of the answer being yes. So it's not a yes no, it's a probability, so 85% or 20% or whatever. So that's when we project it to the left onto the y-axis. And also we can get a predicted value for the dependent variable based on where we select this arbitrary line, 50%. You can select it anywhere you like. You can select it higher, lower, depends on your knowledge about the problem at hand, and as you understand, depending on where you select it, that will significantly affect your variables. So I really hope this explanation was trivial enough and yet insightful enough for you to gain an intuitive understanding of logistic regression. I look forward to seeing you then, and until next time, happy analyzing. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors. And then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right-click, extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. In the following tutorials we will be implementing logistic regression on Python, and I can't wait to show you the final result, to show you how logistic regression manages to separate some categories and predict a binary outcome. So let's start making the model right now, and to start we need to set the working directory. So we have to go to File, Explorer here, and then go to our Machine Learning AZ folder, and part 3 classification, and then logistic regression. Alright, that's the right folder. Make sure that you have your dataset social network ads.csv, and then don't forget to click on this little button here to set the folder as working directory. Alright, and now the real first step of making a machine learning model is to pre-process the data, and to do this, of course, we're going to use the data pre-processing template we've been preparing in part 1. So we're going to copy all this, copy, and paste it here. So now we just need to change a few things. First, let's import the 3 essential libraries. Here we go. And then here we need to change the name of the dataset. Here it's of course social underscore network underscore ads. And now let's select this line to have a look at our dataset. So execute. Perfect. Now let's go to Variable Explorer to have a look at our dataset by double clicking on it here. And here is the dataset. Okay, so just a quick reminder, this dataset contains informations of users in a social network. So those informations are the user ID, the gender, the age, and the estimated salary. And this social network has several business clients which can put their ads on this social network. And one of their clients is a car company who has just launched their brand new luxury SUV for a ridiculous price. And we're trying to see which of these users of the social network are going to buy this brand new SUV. And so the last column here tells if yes or no the user bought this SUV. We are going to build a model that is going to predict if a user is going to buy or not the SUV based on 2 variables, which are going to be the age and the estimated salary. So our matrix of feature is only going to be these 2 columns. We want to find some correlations between the age and the estimated salary of a user and his decision to purchase yes or no the SUV. Okay, so what are the indexes? This is the index 0, index 1, index 2, and index 3. So here we're going to put our indexes. We're going to put our 2 indexes in brackets. So it's 2, comma, and 3. So that's the 2 indexes of the columns that we want to include in our matrix of features. Okay, and what about y? Let's see y. Okay, so this was index 2, index 3, and index 4. So here y is going to take the index 4. Alright, and now we're ready. Let's check if everything's okay. Let's select this. Command and Control plus Enter to execute. And here we go. X and y appeared here. So let's look at them. X. Okay, this is clearly the age here and the estimated salary for all of our 400 observations. Perfect. Okay, and Y. Okay, perfect. Y is the purchase column. 0 means no, the user didn't buy the car, and 1 means yes. Alright, now let's split the data set into the training set and the test set. So which test size would you like to choose? We have 400 observations, so a good test size would be like to have 300 observations in the training set and 100 observations in the test set. Is that cool? Okay, so let's do this. That means that we want to take 0.25, that is 100 observations. Let's select this, Command and Control plus Enter to execute. Alright, so we have now our X train, X test, Y train and Y test, and you can see that we have 300 observations in the training set here and 100 observations in the test set. Okay, great. And now, do we need to apply feature scaling? Well, yes, we're going to do it because we want accurate prediction. We want to predict which users are going to buy the SUV to, target these users as well as possible. So I'm going to remove that multi-line comment here. And I think we're fine. X train and X test are ready to be transformed, to be scaled. So let's select this. Command and Control plus Enter to execute. Okay, perfect. Now let's look at our training set and test set. So as you can see, the X train is well scaled. And okay, so that's for, so Y train wasn't scaled, obviously, because this is the categorical dependent variable. And X test scaled based on the same scale because we fitted the SCX standard scalar object to our matrix of features X train, and we used this same object on X test. So this means that it's scaled on the same basis. Okay, and Y test, of course, it's not scaled. Great, so we are ready. We pre-processed our data correctly, and now we're ready to build our logistic regression model. I can't wait to show you the results. Your intuition is going to get even more shaped by looking at the results because everything is going to be visual. I can't wait to see you in the next tutorial to start. Until then, enjoy machine learning. Hello and welcome to this Python tutorial. So in the previous tutorial we pre-processed our data to make it ready for our model, and therefore today we can start fitting logistic regression to our training set, and that's what we're going to do in this tutorial. So as usual, let's import the correct library for that job, which is going to be the linear model library. And why linear? It's because the logistic regression is a linear classifier, which means that here, since we are in 2 dimensions, our 2 categories of users are going to be separated by a straight line. So you're going to see your intuition of logistic regression is even going to be better shaped when you will find out about the graphic results. So let's import this library by typing from sklearn that linear model, that's the name of the library, here it is. Okay, and then import, we're going to import the right class for it, which is the logistic regression class. Once again, a very intuitive name, we like it. And then, as usual, we're going to create an object from this class, which is going to be our classifier that we're going to fit on our training set. So let's do it. I'm going to create a new variable classifier, which is actually our logistic regression object. And to create this object, I'm going to call the class logistic regression. And here we go. The logistic regression class has several parameters. We can check them by inspecting the logistic regression class. We type Command I to inspect the class. Here we go. As you can see, there are several parameters, but we're not going to use any of them. We're only going to use the random state parameter here just to have the same results. So here I'm going to input random state equals 0 so that we all get the same results. Alright, so our logistic regression object is ready, and now I'm going to take it, classifier, and I'm going to fit it to the training set. And to do this, I'm going to use this method here, which is the fit method, to fit it to our training set. Okay, so enter, fit, and then we want to fit it to our training set. So here we input X train and Y train. Because remember, what this means is that we're taking our logistic regression classifier object, we are fitting it to the training set X train and Y train, so that our classifier learns the correlations between X train and Y train. then by learning those correlations, he will be able to use what he learned to predict new observations. And we're going to test its predictive power on a different set, which is going to be the test set. And that's what we're going to do in the next tutorial. So I'm just going to select here this, Command and Control plus Enter to execute. And here we go. Now our logistic regression model is fitted to the training set. Okay, so that's perfect. Our logistic regression model is fitted to the training set. And now in the next tutorial, we will be predicting the test set results with this logistic regression model. So I look forward to seeing you there, and until then, enjoy machine learning. Hello and welcome to this Python tutorial. So in the previous tutorials we pre-processed our data here, then we fitted logistic regression to the training set, and now today we're going to predict the test set results. So it's going to be very fast, it's going to take us one line, so let's write it. We're going to introduce a new variable here that we're going to call y_pred, because ypred is going to be the vector of predictions. That means that it's going to be the vector that gives the prediction of each of the test set observation. Okay, so let's compute this vector. Simply to compute it, we're going to take our classifier that we created in the previous tutorial, the classifier that was fitted to the training set. And here we're going to use another method of the logistic regression class, because the classifier is an object of the logistic regression class. And this method is going to be this time the predict method. Very simply, here it is, predict. And in parentheses, we have to input an argument. In your opinion, what is this argument going to be? We are going to predict the results of the x-test observation. So here we have to input x-test. Okay, and it's ready. So let's select this line, press Command and Control plus Enter to execute. And here we go. Our vector of predictions ypred is ready. Let's have a look. So ypred is just here. And if we open our test set, you're going to understand what it does. Okay, so remember this was scale, so we cannot interpret this. But here was the age column and here was the salary column. Okay, so let's take for example the first user. Here we have a 0, which means that our logistic regression classifier predicted that this user didn't buy the SUV car. However, if we look at the 7th observation here, so the 7th user, here we have a 1, which means that the logistic regression classifier predicted that this user bought the SUV car. Okay, so let's close this, and that's it for this tutorial. That's how you predict the test set results with our logistic regression classifier. In the next tutorial, we will be evaluating the performance of this logistic regression classifier using the confusion matrix. So we're going to see the number of correct predictions and the number of incorrect predictions that our logistic regression classifier made. So I look forward to seeing you in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this Python tutorial. So in the previous tutorials, we pre-processed our data, we fitted logistic regression to the training set, then we predicted the test set results, and today we're going to evaluate if our logistic regression model learned and understood correctly the correlations in the training set to see if it can make powerful predictions on a new set, especially the test set. So this confusion matrix is going to contain the correct predictions that our model made on the test set, as well as the incorrect predictions. Alright, so let's create this confusion matrix. Once again, it's going to be very fast. And as usual, we're going to import a tool that is going to help us compute this confusion matrix faster. Only this time it's not going to be a class, it's going to be a function, which we will import from the sklearn.matrix library. So let's do it. Let's type from sklearn.matrix import, and then we import our function. Our function is confusion matrix, confusion_matrix. Alright, and you can clearly make the distinction between a class and a function, because remember the class contains capitals at the beginning of the word. So now we're going to use this function to compute the confusion matrix in just one line. So we're going to call our confusion matrix CM, which is a new variable, but it's the confusion matrix. And then we're going to use our function, confusion matrix, that we just imported. Here we go. And then we're going to input the parameters. Alright, so let's inspect the confusion matrix. We press Command I to have a look at the info. Here we go. So that's our parameters. Let's see what parameters we have to input. So the first parameter is y true. So that's the correct values. That's the real values. That's the values of your data set. That's actually what happened in real life. And a cool name to designate it, I like this name, it's ground truth. Ground truth means the real values that happened in reality. Okay, so our first parameter is then y test, because this is the vector of the real values, which are telling if yes or no the user really bought the SUV car. And then what is the second parameter? The second parameter is y pred. So this time it's the vector of predictions. The vector of predictions that our logistic regression model predicted. So do you guess what this is? It's actually y underscore pred. And that's it. That's all we need to know. I know there are several more parameters. Oh, actually there's just one parameter, it's labels, but it's fine. We're not going to use it. We have everything we need here. So let's select these two lines and execute. Alright, the confusion matrix is created. Now let's have a look. To have a look at it, we can go to the console here and type cm and then press enter to have a look at it. Okay, so here's the matrix. We will analyze in much further details the confusion matrix in the final section of this part about evaluating the model performance, but so far I'm just going to tell you that the two numbers here, 65 and 24, are the correct predictions, and those two numbers here, 8 and 3, are the incorrect predictions. So we can see that we have quite a lot of correct predictions. That's good. We have 65 plus 24 equals 89 correct predictions. And we have 8 plus 3 equals 11 incorrect predictions. So that's good. That's a first step into evaluating a model performance. But really the most interesting way to do that, to evaluate a model performance, is what we're going to do in the next tutorial, because we are going to have a graphic visualization of our results, and we will clearly see how our classifier separates the two categories. That means that we will see the decision boundary of the classifier and therefore the decision regions. That means that we're going to clearly see the region where the classifier predicts that the user is going to buy the product, and the other region where the classifier predicts that the user is not going to buy the product. You'll see it's going to be very fun. It's going to be exciting visual graphic results. I can't wait to show you this. So I look forward to seeing you in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this Python tutorial. So that's it, we built our model, we fitted the logistic regression model to our training set, and then we predicted the test set results. We used the confusion matrix to evaluate the predictive power of our logistic regression model. That was actually quite fine. We found 65 plus 24 equals 89 correct predictions, and 8 plus 3 equals 11 incorrect predictions. But that's not really the fun way of visualizing the predictive power. What is much more fun and much more exciting is to look at the results on a graph. So that's what we're going to do in this tutorial. We are going to make a graph where we will clearly see the regions where our logistic regression model predicts yes, the user is going to buy the product, and no, the user is not going to buy the product. So let's make this graph. So unfortunately, we cannot make this graph in just one line or two lines. I tried to make it the simplest as possible, but by doing that I ended up with a little more than 10 lines of code. So what I'm going to do, I'm not going to write the whole code right now because you might fall asleep. So what I'm going to do is I'm going to take the code I prepared to visualize the training set results in my text editor. I'm going to copy it, paste it here, then I will select this code and execute it. We will look at our results, interpret them, and then for those of you interested in how we made such a graph, at the end of the tutorial I will explain how it's making the graph. Okay, so I copied it, I'm gonna paste it now. Here it is, here's the code. So that's 15 lines of code, as you can see. And so since I can't wait to show you the results, we're gonna select the code now, and I'm gonna press Command and Control plus Enter to execute, and we will see the whole thing behind the logistic regression model. We're going to see the true results and the regions of predictions. So let's do it. Command and Control plus Enter to execute. And here we go. That's the graph. So I'm going to enlarge this. And now I'll explain what to interpret. Okay, so let's analyze this graph step by step. First, let's focus on all the points here. We can see that we have some red points and some green points. So all these points that we see on this graph are the observation points of our training set. That is, these are all the users of the social network that were selected to go to the training set. And each of these users here is characterized by its age here on the x-axis and its estimated salary here on the y-axis. Now, we can see that there are some red points here and some green points here. The red points are the training set observations for which the dependent variable purchased is equal to 0. And the green points are the training set observations for which the dependent variable purchased is equal to 1. That means that the red points here are the users who didn't buy the SUV, and the green points here are the users who actually bought the SUV. So now, as a first step of analysis, let's give an interpretation of what we observe here with these users. Okay, so first, we can see that the users who are young with a low estimated salary, so these users here, actually didn't buy the SUV, because these points are the real observation points. They're red, and red corresponds to 0 here. So that means that all these points here are the users who didn't buy the SUV, the users in the training set. Then, if we look at the users who are older and with a higher estimated salary, well, we can see that most of these users actually bought the SUV. And it actually makes sense because the SUV is more like a family car and therefore more interesting for these older users here with a high estimated salary. Besides, we can also see that some older people, even with a low estimated salary, actually bought the SUV. Because we can see that we have some green points here that correspond to an age above the average is here, but an estimated salary below the average, because the average is here. Okay, so these guys, these older guys, although they have a low estimated salary, actually bought the SUV. Probably because they've been saving up some money, or maybe they finished paying up their mortgage. I don't know, but what's for sure is that they couldn't resist buying this very cool luxury SUV offered at a ridiculously low price. And on the other hand, we can also see that there are some young people here with a high estimated salary who actually bought the SUV. You know, maybe because it's a very cool SUV and they want to impress their friends and take them into road trips, or maybe they already have a family, I don't know. Anyway, they bought the SUV. Actually, there are a lot of buyers, so this must be a very cool and cheap SUV. Okay, and now, what is the goal of classification? Now we're talking machine learning. Why are we making some classifiers? And what will classifiers will do? At least what are we trying to make them do for this particular business problem? Well, the goal here is to classify the right users into the right categories. That is, we are trying to make a classifier that will catch the right users into the right category, which are, yes, they buy the SUV, and no, they don't buy the SUV. And we represented the way our classifier catches these users by plotting what are called the prediction regions. And so the prediction regions are the two regions that we see on this graph, this red one here and this green one here. And the red prediction region is the region where our classifier catches all the users that don't buy the SUV. And the green prediction region is the region where our classifier catches all the users that buy the SUV. But be careful, this is according to the classifier. That is, for each user of this red prediction region here, our logistic regression classifier predicts that the user doesn't buy the SUV, and for each user of this green prediction region here, our classifier will predict that the user buys the SUV. Even if that's not the case in real life, that's just a prediction, but that's what our classifier believes will happen. It is the classifier prediction compared to the truth here, which is the point. The point is the truth, and the region here is the prediction. So that makes an awesome tool because for each new user of the social network, Well, our classifier, a logistic regression classifier, will tell, based on its age and its estimated salary, if this user belongs to this red prediction region here and therefore doesn't buy the SUV, or if this user belongs to this green prediction region here and therefore buys the SUV. And that way, this business client car company can substantially optimize their marketing campaign by targeting the social network ads to the users in the green region, because these are the users that are predicted to buy the SUV according to our classifier. Now, the other very important thing to understand is that these are two prediction regions separated by a straight line, which is the straight line here. And the straight line is called the prediction boundary, because it's the boundary between the two prediction regions. And the fact that it's a straight line is not random. It is for a particular reason, and that's the thing very important to understand, because that's the essence of logistic regression. If the prediction boundary is a straight line here, that's because our logistic regression classifier is a linear classifier. That means that here, since we are in 2 dimensions, because we have 2 independent variables, the age and the estimated salary, so we are in 2 dimensions, then since the logistic regression classifier is a linear classifier, then the prediction boundary separator here can only be a straight line. If we were in 3 dimensions, then it would be a straight plan separating 2 spaces. But here in 2 dimensions, it's a straight line. And it will always be a straight line if your classifier is a linear classifier. But you will see later that when we build non-linear classifiers, then the prediction boundary separator won't be a straight line anymore. I won't tell you more right now, and I will let you wait for the surprise. So here, we can clearly see that our logistic regression classifier manages to catch most of the users who didn't buy the SUV in the red region here, and most of the users who bought the SUV in the green region here. So it actually did a pretty good job. However, it seems to have trouble catching some green users here who, in spite of their low salary, bought the luxury SUV, as well as those other green users here who also bought the luxury SUV. Because as you can see, these green points here and those here are in the red region, which is the region where our classifier predicts that the users don't buy the SUV. And those incorrect predictions are due specifically to the fact that our classifier is a linear classifier, and because our users are not linearly distributed. If they were linearly distributed, then we will have all the green points here in this space and all the red points here in this space. And then a linear classifier with a straight line could perfectly separate all the red points here and all the green points here. But here we have some rebellious points who are not in the wanted linear regions, and because our classifier has a linear straight line separator, that's why it has trouble catching those users here and those here. You can clearly see that even if you try to rotate this straight line here, well, you will always have some green points in the wrong category. For example, if we try to rotate here this way, like putting it down, well, okay, we will catch these green points here in the right green region here, but since we rotate it down, we will take more green users here because this will go up, and more green users here will be in the red region. So that's the best separator the logistic regression classifier could find, and it couldn't do better because it can only be a straight line separating these 2 regions. Because to catch those users, the green users here and the green users here in the right category, that is the green region, our classifier would need to make some kind of a curve here to, classify correctly those green users here and place them in a green region. And that would prevent our classifier from making these incorrect predictions here because it is a straight line. With a curve here, we would catch all the red users properly in the red region and all the green users in the green region. So that would make an awesome classifier. And you will see how our non-linear classifiers will make a terrific job at doing this. I can't wait to show you this. Okay, and now eventually the last thing very important to understand is that this is the training set. This is a training set, so that means that our classifier learned how to classify based on these informations here. So I would hold my breath a few more seconds until I find out if our logistic regression classifier can manage to make good predictions of new observations, that is to classify new users into the right regions, which by the way are fixed regions here because these are the regions generated by the learning experience of our logistic regression classifier, and therefore won't change if we look at some new observations, that is, new social network users. And that's what we are about to find out on the test set. So hold on. So what I'm going to do now, I'm going to copy this because we want to be efficient, and paste it here. And now I'm just going to replace training here by test. Alright. And here I just have to replace xtrain by xtest and ytrain by ytest. That's all. That's all I need to do. Oh, and maybe the title. I'm going to change the title of the graph test. Okay, so let's now see how our logistic regression classifier predicts the new observations on the test set on which our model wasn't built. So Command or Control plus Enter to execute, and let's see. Alright, not bad, not bad. I'm going to enlarge this. Here we go. So this looks good. This looks very good. These are the real results in red. That means the users that didn't buy the SUV in reality, and these are the customers that bought it. And we can see that the prediction regions predict well those real values, because all those red points here are in the red region, so that's the correct predictions. All those green points here are in the green region, so that's some other correct predictions. And of course, since this is a linear classifier, the logistic regression makes a few mistakes here, but that's fine. And that's actually the incorrect predictions we saw on the confusion matrix. Remember, there was 11 incorrect predictions. We can count them here. This green point should be here, so it's 1, then 2, 3, 4, 5, 6, 7, 8, and then we have to count the red points in the green region that was incorrectly predicted. So 9, 10, and 11. Okay, so yes, that's the 11 incorrect predictions that we found in the confusion matrix. Alright, so that's the first classification model we built. I hope you like the graph. Okay, so congratulations, you implemented your first classification model on Python. In the next tutorials we're going to do it on R. And now for those of you who are interested in understanding how the graph was made, stay with me and I will explain right now how it works. Okay, so the best way to explain it is to reselect this. I'm going to Control plus Enter to execute, and here's the graph. So what is the idea? How did we plot those prediction regions? Well, the idea is actually pretty cool, because we took all the pixels of this frame here, that means this pixel, all the pixels, but actually with a 0.01 resolution. So we took all the pixel points of this framework and we applied our classifier on it. And so, you know, it's like each of these pixel points is a user of the social network with a salary and an age. So it's like an observation, only it's not the observations we have in our data set, it's a new observation we create. But we have to picture this like a user in the social network with an estimated salary and the age. So for each of these new pixel points, these new pixel observation points, we applied our logistic regression model to predict if this pixel observation point has value 0 or 1. And if our classifier predicts 0, then it's going to colorize this pixel point in red. And if the classifier predicts 1, it's going to colorize the pixel point in green. So by doing this on all the pixel points in the frame here, it colorizes all the pixel points that have the 0 predictions here, and all the pixel points that have the 1 prediction. And since the logistic regression is a classifier, the limits between those sets of points is a straight line, because as I told earlier, the logistic regression is a linear classifier, which means it's a straight line in 2 dimensions. And now that you understand that, you will understand this code very well. Okay, so now let's go through the lines one by one. We start by importing the listed column map class that will help us colorize all the data points. Then we create this line to just create some local variables xset, so that we can replace xtrain and ytrain easily by xtest and ytest instead of having to replace it everywhere, because you know we use xset several times. So you know there's just a shortcut to avoid having to replace too many times the xtest and xtrain here. Okay, here with these two lines of code, x1 and x2 equals np.meshGrid, we prepare the grids, with all the pixel points that I just talked to you about. So here, as you can see, we take the minimum values of the age values, -1 because we don't want our points to be squeezed on the axis here, and the maximum values of the age, to get the range of pixels we want to include in the frame. And same for the salary, we're taking the minimum salary -1 and the maximum salary +1 to get all the estimated salary range, and -1 and +1, so that the points aren't squeezed. And here we're choosing the steps 0.01, that means that there is a 0.01 resolution. So for example, if I had chosen 0.5, this wouldn't have been that dense. We would actually see the pixel points. But that's better to take this resolution because these are nice prediction regions. It's like it's continuous. Okay, and then with this line of code, that's where the whole magic happens. Because this is where we apply the classifier on all the pixel observation points. And by doing that, it colorizes all the red pixel points and all the green pixel points. And we use this contour function to actually make the contour between the two prediction regions, the red one and the green one. Then as you can see here, we use the predict function of our classifier, the logistic regression classifier, to predict if each of the pixel points belongs to class 0 or class 1. Then if the pixel point belongs to class 0, it will be colorized in red, and if the pixel point belongs to class 1, it will be colorized in green. Okay, so here we plot the limits of x, the age, and y, the estimated salary. Then with this loop here, we plot all the data points that are the real values. So all the red data points here and the green data points. So we're using this plt.scatter, which is what we use from matplotlib to make a scatter plot. And then very simply here we add the title, logistic regression training set, the x label age, the y label estimated salary. We plot the legend to specify that the red points correspond to 0, that is the user didn't buy, and the green point corresponds to 1, that is the user bought the product. And plt show to display the graph and specify that this is the end of the graph. Alright, so congratulations if you're still here. Congratulations for having the curiosity of wondering how we can build such a plot. So that's a lot of things to learn in this section, because you learn how to make a logistic regression model and how to make an awesome chart. So congratulations. After we do the same thing on R, in the next sections things are going to get even more exciting, because we will build even more powerful classifiers. So I look forward to showing that to you, and until then, enjoy machine learning! Hello and welcome to this Python tutorial. So this is not exactly a Python tutorial, because what we'll do in this tutorial is just to make a classification template. And we're doing this because the future classification models that we're going to build are going to be built much more efficiently thanks to this template we're making in this tutorial. And we will make this template from our logistic regression model, because as you can notice in this model that we just built in this section, well, the only time that we code something about logistic regression specifically is just in this section. Indeed, the rest is purely generalized. For example, when we predict the test set results, we don't use any class or function specific to the logistic regression. We use this classifier here, which is indeed the classifier of logistic regression, but what we'll do in the next sections when we build other classification models will be only to import a new class that will be the required class to build our future classification models, and then we will call this class here to create our classifier object, which we will still call classifier, and then we will use the fit method. But that's the only part of the whole code where we talk specifically about the model. Nowhere else in the code has something specific to logistic regression. For example, here I don't use anything about logistic regression, I only use the classifier here, but our future models will be called classifier as well. And same for this last section here, I don't talk about logistic regression, I don't code anything specific to logistic regression, only this classifier here. So that's why it's really easy for us to make a template for the future models, and that's why we will be so efficient at creating the future classification models thanks to this specific template. So let's make the template. We will actually take everything from here to the bottom, copy, and paste it here. And now what we have to do is only to remove this part of the code here, because This is specific to the logistic regression model, so we will remove this section and replace it by a comment to specify that we need to create our classifier right here. And then we can generalize even more by replacing logistic regression in the title of this section here by the classifier. Alright, and actually that's all. Our template for classification is ready to build very efficiently any new classification model. And you will see that in the next sections. You will see how we will only have to create our classifier here in 3 lines in this section, and we will be ready to make the prediction, visualize the training set results, and visualize the test set results. So actually, speaking about that, let's recap about what this template is doing. So in the first section we import the libraries, NumPy, Matplotlib, and pandas. In the second section we import the dataset, our social network ads dataset. Then in the third section we split the dataset into the training set and the test set. Then in the next section we have this code to apply feature scaling if we need to. Then this is in the section that we create our classifier. So we will create many classifiers. We will create the SVM, the kernel SVM, naive Bayes, decision tree classification, random forest classification, a lot of classifiers for this same specific business problem. And then once our classifier is created, we predict the test set results, then we make the confusion matrix, and then my favorite part, we visualize the training set results, and same as for the test set results that we will also visualize to make sure that we don't have any overfitting and that the performance of our model is still good on new observations. So here we are, ready to build new classification models very efficiently. I look forward to creating these new models with you, and until then, enjoy machine learning! Hello and welcome to this R tutorial. In the previous tutorials we implemented our logistic regression model on Python, and this time we're going to do it on R. So the first thing that we need to do is to set a working directory. Right now I'm on my desktop, so let's go to the machine learning AZ folder, part 3 classification, section logistic regression, and here we are on the right folder. So that's the folder to set as working directory. Let's make sure we have the social network ads CSV file, all good. So I'm gonna click on this more button here to set this folder as working directory. And here we go, everything is fine, we're ready to start making the model. So the first step as usual is to pre-process the data, and to do this of course we're gonna use our data pre-processing template that we made in part 1. So I'm going to select all this, copy, and then I'm gonna go back to my logistic regression file to paste it here. Alright, and now we just need to change a few things to pre-process our data. That's of course the name of the dataset here, which is social network ads. Alright, and then we need to change another few more things, but first let's select this line to see what our dataset looks like. So Command and Control plus Enter to execute. Here we go, the dataset is well imported. Let's click on that, and here's the dataset. So as a quick reminder, this dataset contains informations of users of a social network. These informations are the user ID, the gender, the age, and the estimated salary. And the social network has several business clients, and these business clients put ads on the social network for marketing campaigns purposes. And one of their business clients is a car company who has just launched its brand new luxury SUV at a ridiculous price. So this car company put ads of their new SUV product on the social network, and then the social network gathered some information about which users responded positively to the ad by buying the product, and those who responded negatively by not buying the product. So that's what the last column is about. The last column tells for each user if the user bought the car, and then it's a 1, or didn't buy the car, and then it's a 0. Alright, so that's the business problem itself, and now our mission is to make a logistic regression model that will try to understand the correlations between information such as the age and the salary, and the decision of the user to buy, yes or no, the SUV. Alright, so let's go back to our logistic regression model, and let's see what we need to change next. So this line is to select the variables we want to train our model with. So as I just said, we're going to train our model with only the age and the salary. So that means that we want to predict if the user is going to buy the SUV based on only the age and the salary. So here we will need to select the indexes of the columns we want to take for our model. So I'm going to remove that as comment, and let's look at the indexes. Okay, so indexes in R start at 1, so that's 1, 2, 3, 4 and 5. So we only want to take the indexes 3, 4 and 5. So let's do this. We're going to choose from 3 to 5. Alright, so now let's select this and execute. Alright, and now if we go back to our data set, you can see that we only have our 3 columns of interest, which are the age, the salary, and purchased. Okay, now next step. Next step is to split the data set into the training set and the test set. And here, what we only need to change is the split ratio, or maybe not. But we have 400 observations. I think a good split would be to have 300 observations in the training set and 100 observations in the test set. And to do this, we need to take 0.75, that is 75%, going to the training set, that is 300 observations. Okay, so let's select this and Command and Control plus Enter to execute. Here we go. Now let's look at our training set and our test set. Alright, so our training set, as you can see, has 300 observations, and the test set has 100 observations listed here. Perfect. Now let's go back to our logistic regression and take care of the next step, which is the feature scaling. So for classification, it's better to do feature scaling. So we're going to do it. We're going to remove those comments here by pressing Command and Control plus Shift plus C. Alright, and now let's check that we have the right indexes. Here we have indexes 2 and 3. Here the dependent variable is categorical. So we will only scale this, and that's index 1 and 2. So let's go back to our logistic regression model. And so here we need to choose 1, 2, 2. Let's do it for the 4, 2, 1, 2, and 1, 2. Alright, let's select this. Command and Control plus Enter to execute. And here we go. Now let's have a look at our training set. Yep, the age and the salary are perfectly scaled, and same for the test set. Perfect, perfectly scaled. Alright, so we're done with the data preprocessing phase. Now our data set is well preprocessed. So that's the end of this tutorial. I can't wait to build this logistic regression model on our data set that is now prepared in the next tutorials. Until then, enjoy machine learning. Hello and welcome to this R tutorial. So in a previous tutorial we just pre-processed our dataset to make it ready for our logistic regression model that we will fit on the training set. So that's what we're going to do in this tutorial, and let's do it right now. So it's going to be very simple. We're just going to create our classifier equals, and then we're going to use an existing function of R called the GLM function that is going to build this logistic regression classifier. So let's type here GLM, and then let's press F1 to see what parameters we have to input. Okay, so the first thing we see is that GLM is for generalized linear models, and that's because the logistic regression is a linear classifier. For those of you who didn't follow the Python tutorial, you will see that our logistic regression classifier will linearly separate our two classes of users. And then let's look at the arguments to see what we have to input. Alright, so the first argument is formula. So that's the same as what we did in the regression section. Here we're going to write formula equals, and then we take the dependent variable, which is purchased, then out plus n, and then here a dot to specify that we want to take all the independent variables. So that way R understands that we want to predict the purchased result based on all the independent variables, which are the age and the estimated salary. Alright, now what is the next argument? So let's add a comma here, enter, and let's add the second argument. So the second argument is family, and here, since we are in logistic regression, we're going to add family equals binomial. So at this stage, it's not important to understand what binomial means exactly, but you just have to remember that for logistic regression, you have to specify the binomial family here. And then we just need to input one last argument. It's the data here, which is the data on which you want to train your logistic regression model. So of course, that's our training set. So we're going to add here data equals training set. Here we go. Here it is. Okay. And that's it. By only using this GLM function and precising the formula, the family, and the fact that we're building the model on the training set, that builds our logistic regression classifier. So now let's select this. Command and Control plus Enter to execute. And here we go. The classifier is built. Okay, so that's it for this tutorial. We fitted logistic regression to the training set, and in the next tutorial we will be predicting the test set results using this classifier that we just built. Alright, thank you for watching this tutorial. I look forward to seeing you in the next one, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So now that we fitted our logistic regression to the training set, we are going to predict the test set results using this classifier that we just built in the previous tutorial. So usually we can do this in one step, but for logistic regression we're going to do it in 2 steps, and we are more interested in having the 0 and 1 predictions rather than the probabilities. So first let's take anyway the probabilities. So we're going to call them pred, which is the vector of the which will be the vector of the predicted probabilities of our test set observations by the classifier. So pred equals predict. So we're going to use this predict function to predict the probabilities based on our GLM classifier. And speaking of classifier, this is our first argument in the predict function. So here we input classifier, comma. Then the next argument is type. And for logistic regression, we should choose the response type, because that will give us the probabilities listed in a single vector. So that's what we want. And then we have to specify the new observations that we want to predict. So in our case, these new observations are the test set observations. So new data equals test set. And we're just going to remove the last column of the test set, because the last column is the dependent variable and that's what we want to predict. So we will only take test set minus 3, that is the 2 independent variables, age and salary of the test set. Alright, so let's just summarize this line. We are predicting the test set observations using our classifier, which is the logistic regression classifier. Alright, but that returns the probabilities, because as you can see, if I select this line and execute, here if I type pred in the console, I will get, as you can see, I will get the probabilities of each of my test set observations. So here, for example, let's go to our test set. The first observation has index 2. The real result is 0. That means that the user number 2 didn't buy the SUV. And now if we go back to logistic regression, we can see that for this user number 2, pred returned 0.016. So what is this probability exactly? This probability is the probability that the dependent variable is equal to 1. That is the probability that the user buys the SUV. So here, since it's very small, it's 0.016, that means that the classifier predicts a very low probability of the dependent variable being equal to 1. That means that it predicts that the user number 2 has very low chance to buy the SUV. Therefore, in short, pred returns the predicted probabilities that the user will buy the SUV. But we don't really want that. We would rather have the 0 and 1 results. And to do this, it's very simple. We're just going to do some kind of a conversion. So we're going to create our vector of predicted results that we're going to call ypred equals, and then we're just going to use if-else to transform those probabilities into 0 and 1 results. So here I'm going to write if-else. So the first argument of if-else is the condition, and the condition is going to be pred over 0.5. Because if prop_pred is larger than 0.5, that means that the user has more chance to buy the SUV. So in that case, that means that we want to predict 1. And actually the second argument of the if-else function is the result you want to take when this condition is true. So here we're going to put a 1. Alright? And the last argument is the result you want to return if this condition is false. And if this condition is false, that means that the predicted probability is lower than 0.5. That means that the user has less chance to buy the SUV, and therefore it's going to be a 0. And that's it. Now you're going to see, if I select this line and execute, alright, let's look at ypred now. Ypred, as you can see, I only have zeros or 1. I no longer have the probabilities. And remember, the real result for user 2 was 0, so that's what happened in reality. And here our classifier predicted 0, so that's a correct prediction, and that's because, remember, before the probability was very low, so it was below 0.5, and therefore it returned 0. Alright, so we predicted our test set results. That's a good thing. Now we are going to evaluate these predictions thanks to the confusion matrix that we're going to build in the next tutorial. So I look forward to seeing you there, and until then, enjoy machine learning! Hello and welcome to this R tutorial. So in the previous tutorial we predicted our test set results, and now in this tutorial we are going to evaluate those predictions by making the confusion matrix, which will count the number of correct predictions and the number of incorrect predictions. So let's do it. Let's make the matrix. It's very simple. It will just take us one line. So let's call it CM equals. Then very practically we're going to use the table function in R. And in this table I will first input the real values, which are the test set brackets, and then I have to select the columns of the real results, which is, if we go to the test set, this column, because this column contains the real results whether the user bought yes or no the SUV, and this column has index 3, so here I will put comma and 3. Alright, so that's my first argument, that's the real values, and then as a second argument I'm going to input the predicted values, which is of course the ypred vector here. So here I'm going to add ypred. And I don't have to select any index because ypred is already the vector of predictions. So in short, this is the vector of real values for all the observations, and this is the vector of predictions for the same observations as in this vector. Okay, and that's it. The confusion matrix is ready. So now let's select this line and execute. Here it is, table created. Now let's go to the console and have a look at it. CM, enter, and here it is. The most important thing to understand here is that the 57 and the 26 here are the correct predictions, and the 10 and the 7 here are the incorrect predictions. So what's interesting here at first sight is that the classifier made 57 plus 26 equals 83 correct predictions, and 10 plus 7 equals 17 incorrect predictions. Alright, so 17 incorrect predictions on the test set. That's not bad, but we can do better, and we will do better with other classifiers. You'll see that in the next sections. Okay, so we're done with the confusion matrix. And finally, now it's time for the best part, because in the next tutorial we will be graphically looking at our results, because we will plot this very cool chart that will allow us to make an awesome interpretation of the results. So I look forward to seeing you in the next tutorial where we will make this chart. Until then, enjoy machine learning! Hello and welcome to the final round of logistic regression. So let's recap what we did in the previous tutorials. We started by pre-processing our data using our data pre-processing template, and that made our data set ready to fit the logistic regression to our training set, which is what we did in this step. Then we used this logistic regression classifier to predict the test set results. so that we can evaluate the predicting power of our logistic regression model. And then indeed we made this confusion matrix to actually count all the correct predictions and the incorrect predictions. And now we're at the final step, which is to visualize the training set results and the test set results as well. And now we're eventually at the final round of our logistic regression model, which is the fun part. Because we're going to visualize the training set results as well as the test set results. And basically we're going to make a plot that will represent everything that is happening with our logistic regression model. So let's make this chart. I'm going to do like in Python. I'm going to take the code that I've prepared and paste it here. I will select and execute the code. And then for those of you who are interested in the idea behind the code, that is how the code plots the graph, I will explain how the code works at the end of this tutorial. Okay, so let's do it. Let's start getting the fun. Okay, so right now I'm going to paste the code. Here we go. Okay, so the first thing to do here is to notice that there is this lm-stat-learn package that you need to install if it's not in your packages here. So as you can see, it's in my packages list because I installed it before. If it's not here, you need to install it. So to install it, you will need to remove this comment and you type install.packages and then in parentheses lm-stat-learn, that's the name of the package, in quotes. Then you select this line and execute. And right now, as you can see, it's installing the package. And now the package is installed. I didn't have to do it because it was already installed, but that was just to show you. And now we're ready to select the code and execute it. And that is even if it's not selected here because I put the library lm-stat-learn, which once executed will activate this package. We'll select it. Okay, then this code contains 15 lines of code. That was also the case in Python, and that's because it's the exact same code based on the same idea. And I will explain this idea, that means I will explain how this code works at the end of this tutorial. But for now, let's select this code and let's see what happens. So Command or Control plus Enter to execute, and let's wait. It's taking a little time, that's normal, but it's gonna plot something. There it is, that's the plot. Okay, so for those of you who followed the Python tutorial, we obtained exactly the same plot. So let's describe this plot. I'm going to enlarge this. Okay, so let's analyze this graph step by step. First, let's focus on all the points here. You can see that we have some red points and some green points. So all these points that we see on this graph are the observation points of our training set. That is, these are all the users of the social network that were selected to go to the training set. And each of these users here is characterized by its age here on the x-axis and its estimated salary here on the y-axis. Now, we can see that there are some red points here and some green points here. The red points are the training set observations for which the dependent variable purchased is equal to 0. And the green points are the training set observations for which the dependent variable purchased is equal to 1. That means that the red points here are the users who didn't buy the SUV, and the green points here are the users who actually bought the SUV. So now, as a first step of analysis, let's give an interpretation of what we observe here with these users. Okay, so first, we can see that the users who are young with a low estimated salary, so these users here, actually didn't buy the SUV. Then, if we look at the users who are older and with a higher estimated salary, well, we can see that most of these users actually bought the SUV. And it actually makes sense because the SUV is more like a family car and therefore more interesting for these older users here with a high estimated salary. Besides, we can also see that some older people, even with a low estimated salary, actually bought the SUV. Because we can see that we have some green points here that correspond to an age above the average is here, but an estimated salary below the average, because the average is here. Okay? So these guys, these older guys, although they have a low estimated salary, actually bought the SUV. Probably because they've been saving up some money, or maybe they finished paying off their mortgage. I don't know, but what's for sure is that they couldn't resist buying this very cool luxury SUV offered at a ridiculously low price. And on the other hand, we can also see that there are some young people here with a high estimated salary who actually bought the SUV. You know, maybe because it's a very cool SUV and they want to impress their friends and take them into road trips, or maybe they already have a family, I don't know. Anyway, they bought the SUV. Actually, there are a lot of buyers, so this must be a very cool and cheap SUV. Okay, and now what is the goal of classification? Now we're talking machine learning. Why are we making some classifiers, and what will classifiers do? At least what are we trying to make them do for this particular business problem? Well, the goal here is to classify the right users into the right categories. That is, we are trying to make a classifier that will catch the right users into the right category, which are, yes, they buy the SUV, and no, they don't buy the SUV. And we represented the way our classifier catches these users by plotting what are called the prediction regions. And so the prediction regions are the two regions that we see on this graph, this red one here and this green one here. And the red prediction region is the region where our classifier catches all the users that don't buy the SUV. And the green prediction region is the region where our classifier catches all the users that buy the SUV. But be careful, this is according to the classifier. That is, for each user of this red prediction region here, our logistic regression classifier predicts that the user doesn't buy the SUV, and for each user of this green prediction region here, our classifier will predict that the user buys the SUV. Even if that's not the case in real life, that's just a prediction, but that's what our classifier believes will happen. It is the classifier prediction compared to the truth here, which is the point. The point is the truth, and the region here is the prediction. So that makes an awesome tool, because for each new user of the social network, well, our classifier, a logistic regression classifier, will tell, based on its age and its estimated salary, if this user belongs to this red prediction region here, and therefore doesn't buy the SUV, or if this user belongs to this green prediction region here, and therefore buys the SUV. And that way, this business client car company can substantially optimize their marketing campaign by targeting the social network ads to the users in the green region, because these are the users that are predicted to buy the SUV according to our classifier. Now, the other very important thing to understand is that these are two prediction regions separated by a straight line, which is the straight line here. And the straight line is called the prediction boundary, because it's the boundary between the two prediction regions. And the fact that it's a straight line is not random. It is for a particular reason, and that's the thing very important to understand, because that's the essence of logistic regression. If the prediction boundary is a straight line here, that's because our logistic regression classifier is a linear classifier. That means that here, since we are in 2 dimensions, because we have 2 independent variables, the age and the estimated salary, so we are in 2 dimensions, then since the logistic regression classifier is a linear classifier, then the prediction boundary separator here can only be a straight line. If we were in 3 dimensions, then it would be a straight plan separating 2 spaces. But here in 2 dimensions, it's a straight line. And it will always be a straight line if your classifier is a linear classifier. But you will see later that when we build non-linear classifiers, then the prediction boundary separator won't be a straight line anymore. I won't tell you more right now, and I will let you wait for the surprise. So here, we can clearly see that our logistic regression classifier manages to catch most of the users who didn't buy the SUV in the red region here, and most of the users who bought the SUV in the green region here. So it actually did a pretty good job. However, it seems to have trouble catching some green users here who, in spite of their low salary, bought the luxury SUV, as well as those other green users here who also bought the luxury SUV. Because as you can see, these green points here and those here are in the red region, which is the region where our classifier predicts that the users don't buy the SUV. And those incorrect predictions are due specifically to the fact that our classifier is a linear classifier, and because our users are not linearly distributed. If they were linearly distributed, then we will have all the green points here in this space and all the red points here in this space. and then a linear classifier with a straight line could perfectly separate all the red points here and all the green points here. But here we have some rebellious points who are not in the wanted linear regions, and because our classifier has a linear straight line separator, that's why it has trouble catching those users here and those here. You can clearly see that even if you try to rotate this straight line here, well, you will always have some green points in the wrong category. For example, if we try to rotate here this way, like putting it down, well, okay, we will catch these green points here in the right green region here, but since we rotate it down, we will take more green users here because this will go up, and more green users here will be in the red region. So that's the best separator the logistic regression classifier could find, and it couldn't do better because it can only be a straight line separating these two regions. Because to catch those users, the green users here and the green users here in the right category, that is the green region, our classifier would need to make some kind of a curve here to, classify correctly those green users here and place them in a green region. And that would prevent our classifier from making this incorrect predictions here because it is a straight line. With a curve here, we would catch all the red users properly in the red region and all the green users in the green region. So that would make an awesome classifier. And you will see how our nonlinear classifiers will make a terrific job at doing this. I can't wait to show you this. Okay, and now eventually the last thing very important to understand is that this is the training set. This is a training set, so that means that our classifier learned how to classify based on these informations here. So I would hold my breath a few more seconds until I find out if our logistic regression classifier can manage to make good predictions of new observations, that is to classify new users into the right regions, which by the way are fixed regions here because these are the regions generated by the learning experience of our logistic regression classifier, and therefore won't change if we look at some new observations, that is new social network users. And that's what we are about to find out on the test set. So hold on. So it's very simple. We're just going to copy all this code section here, paste it here, and I'm just going to change the training set here by test set. Same here, I changed training set by test set, and that's all. That's all because I structured the codes in such a way that we only need to change the training set into the test set here to plot this graph on a specific set. However, let's change the title here because we want to specify that it's the test set, and it's ready. So let's select this and execute. Let's see what happens. And here are the results of the test set. So that's not too bad. That's not too bad because as we can see, the majority of red points are in the right region. That means the region predicted to be 0. And the majority of green points are in the right region. As for the training set, there are some observations that were incorrectly predicted. That's normal, that's because it's a linear classifier and it cannot make a curve here catching all the right guys. And remember, in the confusion matrix we counted 10 plus 7 incorrect predictions. And if you want to count the incorrect predictions here, you will find 17 incorrect predictions. Alright, so that's it for the interpretation of the graph. I can't wait to show you how we can make more powerful classifiers, so it's going to be in the next sections, and of course these are going to be nonlinear classifiers. So for those of you who are interested in knowing how the code works, stay with me, I will explain that. So I will reduce this, okay, and let's explain this. Okay, so the idea is that we consider each of these pixel observation points as a user in the social network, like an imaginative user. And so, for example, this pixel point here is not a user in the dataset, but we imagine this pixel point here as a user who has this salary and this age. And we apply our classifier on this pixel observation point, on this user here, so that the classifier predicts if the user is going to buy yes or no the SUV. Then once the classifier makes its prediction, it colorizes the pixel observation point according to the prediction. So if the prediction is no, this pixel user won't buy the SUV, then it will colorize in red. And if the prediction is yes, this pixel user will buy the SUV, then it will colorize the points in green. And so we applied that idea on all the pixels in this frame, so that eventually our classifier will colorize all the points that he predicted as 0 in red and all the points that he predicted as 1 in green. So now that you get the idea, let's look at our code here and go through the steps of completing this idea. Okay, so first I declare set equals training set. That's because, I want to plot this graph for the training set and the test set. And since we're using training set many times in the code, I just replaced it by set here, so that when I copy paste the same code for the test set, I just need to replace test set by training set only here and not in the whole code. So basically that's just a shortcut. And so first we build a grid with x1 and x2. So we take the minimum of the values of the training set -1 because we don't want the points to be squeezed in the graph, and same for the maximum +1. So by doing this we're taking the range of our training set observation points -1 and +1 so that our points are not squeezed in the graph. And so we're doing this for the age column of the training set and the salary column of the training set. Then by writing this line we are building the grid. So basically with these 3 lines we're making the grid here with all the pixel observation points that are imaginary social network users. Then since this grid set is actually a matrix of the 2 columns age and salary, but for all the imaginary users that are the pixel observation points, this is actually a matrix. So with this line we just give a name to the columns of this matrix, which are age and estimated salary. And then that's where all the magic happens. Because here that's where we use our classifier to predict the result of each of the pixel observation points that are the imaginary pixel users. So we predict this, and then since the predict function returns the probabilities, we transform it into 1 or 0 result. So that's why I call it Y-grid, because it's the predictions of all the points in the grid. So that returns the vector of predictions of all the points in the grid. And then finally we plot the whole graph. So in this plot we include all our real users and their real actions, red if they didn't buy the car and green if they bought the car, and we plot the predicted results of all the pixel observation points that we created when we created the grid. So that's here, and so I'm using the color spring green, so that is the spring green color, and tomato, that is the tomato color. And for the real points I just use a green 4, which is a color in R, and red 3. So this color is green 4 and this color is red 3. And that's it. That's the idea behind this code. It's totally fine if you didn't understand some things in this code, because anyway we're going to use this code as a template for our next classifiers, and so we'll just have to copy paste this code, but that's all. So that was just for those of you who are interested in coding, who are interested in how we can use code to make such a plot. But the important thing to understand here is that the logistic regression is a linear classifier, which in 2 dimensions means that it's a linear separator, and therefore it can miss some predictions, like the predictions here, that are incorrect. Alright, so thank you for watching this R tutorials, and congratulations, now you know how to implement a logistic regression model using R. This is the beginning of our journey in the classifiers world. You're gonna see that we will meet some more powerful classifiers later in our journey, so I look forward to continue this journey, and until then, enjoy machine learning! Hello and welcome to this R tutorial. So this tutorial is not going to be like the usual ones, because basically what we're going to do is just make a template in order to build our future classification models more efficiently, because indeed we already built our first classification model, which is the logistic regression model, and in the future sections we're going to build new classification models like the SVM, support vector machine, kernel SVM, naive Bayes, decision tree classification, as well as random forest classification. And so we will build these models on the same dataset, the social network ads dataset, and so we will make one template for all our future classification models. So right now, let's make our classification template. And maybe you already noticed that we're going to make this template very easily, because the only part of the code where we code something specific to logistic regression is only in this part, because we use the GLM function to create our logistic regression classifier, but then in the other sections, everything is purely generalized. You know, we use our classifier variable here, which is indeed in this code the logistic regression classifier, but in the next sections, this classifier is going to be something else. And same in this section here, we don't code anything specifically related to logistic regression. Same in this section here about the visualization of the training set results. The only variable that we use is classifier, so nothing directly related to logistic regression. And same for this section here. The only variable that we use is classifier, and so if we give another definition to our classifier here, then this code here will be perfectly adaptable to this new classifier we will be making in the future sections. So that's why it's so simple, and therefore it's worth doing that for the next models we'll be creating. So I'm gonna take everything from here to the bottom, copy, and paste it here in my future classification template. And now our classification template is almost ready. We just need to remove this section here because this is directly related to logistic regression, because here we're using the GLM function that is only used to build a logistic regression model. But you know, in the next sections for the next classifiers we'll be making, well, we'll have this classifier variable here that will be the classifier of our future classification models. And then here, you know, we will use the right function needed to build this classification model, and then all the rest will be ready. We will have our new classifier defined here. Then, since we have classifier here in the predict function, well, we won't have anything to change here. And same for here, and same for here as well, because the only variable that we use is classifier, and that will be defined as the classifier of a new classification model. So let's remember that, and let's, you know, to remind us of what we need to do, I'll just add a comment here to say that it's the section where we create our classifier here. Alright, so that's the section where you create your classifier, and by the way, you can totally use this template on your datasets and your business problems. You will just need to change the name of the dataset and pick your columns of interest, and then just change the name of the dependent variable here and here as well. But then what you will only need to do is to create your classifier here, so you will pick the classifier you want, and then everything will be ready. You will be able to predict the test set results here. Well, be careful of the index here, and make the confusion matrix, and visualize your training set and test set results. So you can totally use this template as well for your data sets, and definitely this template is ready to build the future classification models we will build in this part. So here we go, template ready. Well, we can still generalize it even more by replacing logistic regression here by classifier, and also we can replace logistic regression here by classifier, and here as well. And now the template is fully ready and fully generalized. So you will see how we will be so efficient at building the future classification models. I look forward to creating these models with you, and until then, enjoy machine learning.